Can you hear us?
I can hear you. Can you hear me?
Yeah, we can.
Yeah.
Right. Okay. But how are things going?
Good.
Good.
Yeah.
All right. I thought of an answer to one of the questions from yesterday about vertex transitive graphs with just the 3 points.
Yeah.
There are infinitely many. So, for example, if we take, let's take a graph that has, let's just take a tree. A tree where every vertex has 4 neighbors.
Yeah.
And then we do the same trick of replacing the vertex by something, but now we replace every vertex by a square.
Oh, then it'll become 3 disjoint points.
Yeah. Right. So now if we look at a vertex, it's neighborhood just like that. So it's the cone or the graph with center one vertex and the sphere or the set of vertices with distance 1 away.
Yeah.
So and there are infinitely many graphs, vertex transitive graphs, where that have degree 4, and so there are infinitely many graphs we can obtain in this way. Now we have to be a little bit careful because drawing a square here puts a constraint on the way we can move these edges, right? We can't just permute them arbitrarily anymore. It puts an order on them, and we can only rotate or reflect. But with a regular tree, that's okay. That restriction does still leaves us with a vertex transitive graph. There are other graphs where every vertex has degree 4, where if we then filled in the square, we would not obtain a vertex transitive graph. I think that's true. I haven't thought of an example, but we do have to be careful that we don't in thinking that we automatically get a vertex transitive graph in this way. We don't always, but for a tree, for example, and for many other finite graphs, we do. Right, so what about the path of length 4, or the graph with the line with 5 vertices? Did you think any more about that one? Not really?
Yeah, we can think, but we can't really get a result.
No, it seems to be very hard to face that one. How did you get on with the graphs with 4 vertices? Did you work those out?
Sure. No.
So there's like we got the cases down 5. So.
Sorry?
We listed the cases out for the spheres. 5 edges, 4 edges, 3 edges, 2 edges, and 1 edge.
Yeah.
Yeah. 4. Yeah. I'm not sure if it's complete.
That's
Right. So you still have some to go?
Yeah.
Right. Okay, well, I guess, so you're just going to continue with that? Would that be the plan, to continue with the graphs with 4 vertices, see if you can work them all out and write them up?
Yep.
Right. Do you have some other questions to, well, I think that's enough to be going on with, but do you have any other questions you want to talk about?
So, I don't think so.
Right, okay. Well, maybe just go back to working on these 4 graphs with 4 vertices then. We can meet this afternoon. I might meet with another of the research assistants who, the one who's proved these results about conditions that prevent a graph from being a one sphere in a vertex transitive graph. For example, the result about complete bipartite graphs.
Oh yeah, that would be really interesting.
Yeah, I might meet with him this afternoon, and perhaps we can meet after that. Well, I'll need to go home just before 4, so we're going to meet at 3.
Yeah, sure.
Yeah, okay.
Right, okay. We'll meet then. Looks like you got a sore tooth.
Yeah, it hurts a lot.
Yeah,
It's
maybe.
been bothering the whole day, and yesterday as well.
Right. Maybe you need to get it looked at. What was I going to say? Oh yeah, tomorrow I'm going to have meetings all morning. So we'll meet this afternoon, but then we perhaps our next meeting after that will be tomorrow afternoon.
Yeah, okay.
Okay.
Okay. All right. Well, I'll see you this afternoon then.
Yeah.
Yep, see you.
Yeah. Yep.
Alright, stop recording.